In this video, I want to explore the center of mass in two dimensions. When I have a two-dimensional object, we need to be able to determine, or at least be given, some kind of density or density function in the form of rho is equal to xy that will be defined over a closed region R in the xy plane. In two dimensions, density will have units of mass per unit area, such as a kilogram per meter squared. A two-dimensional region is a representation of a thin plate that we could call a lamina. The center of mass is the point at which a pivot has to be located in order to balance the lamina. If the density is constant, then my center of mass will depend only on the shape of the lamina, and then the center of mass is called a centroid. For multidimensional objects, the coordinates for the center of mass have to be computed separately by treating each coordinate as a one-dimensional problem on its own. The mass of my lamina will be the integral of the density function over the region R. M is equal to the double integral over my region R of rho of xy dA. Now that I have a two-dimensional object, we can define two moments, one which is the moment about the y-axis and one which will be the moment about the x-axis. Be careful here. The moment about the y-axis is given by capital M sub y is equal to m sub 1 x sub 1 plus m sub 2 x sub 2 plus all the other terms up to m sub n x sub n. Notice that this is the moment about the y-axis, which involves my x coordinates. My moment about the x-axis, specified capital M sub x, is equal to m sub 1 y sub 1 plus m sub 2 y sub 2, and so on up to m sub n y sub n. Again, if I imagine just looking around the x-axis, all of my positions will be given in terms of the coordinate y. So if I let rho be an integrable area density function defined over a closed bounded region R in the space R2, the coordinates of the center of mass of the object represented by the region R will be given by x bar is equal to capital M sub y over little m, which is equal to 1 over little m times the double integral over the region R of x times rho of xy dA, and y bar is equal to capital M sub x over little m, which is equal to 1 over little m times the double integral over the region R of y times rho of xy dA, where little m is the total mass and m sub y and m sub x are the moments with respect to the x-axis and y-axis respectively. When my density rho is constant, the center of mass is called the centroid, and it is independent of the density itself. For two- and three-dimensional objects, my center of mass may not actually lie within the object itself. In order to work with center of mass, we want to keep things as simple as possible. We get to choose how to set up our coordinate system. So we always want to look for opportunities where symmetry can be used to eliminate at least one of the integrals in the center of mass calculation. And don't forget what you already know. Mass and area can often be found using simple geometric formulas if the density happens to be constant. Let's work an example. I want to find the mass and centroid or center of mass of the lamina region bounded by y is equal to e to the x, y is equal to e to the negative x is equal to 0, and x is equal to the natural log of 2. We're assuming that I have a constant density here. I want to sketch the region corresponding to the lamina and indicate the location of the center of mass. I want to also use symmetry if I possibly can to simplify my work. Since our density is constant, we can assume it is 1. This means that little m will be equal to the integral from 0 to the natural log of 2 of the integral from e to the negative x to e to the x of 1 dy dx. This is equal to the integral from 0 to the natural log of 2 of e to the x minus e to the negative x dx. I do that integration, evaluated from 0 to the natural log of 2. This gives me 1/2 for my total mass. Now, using 1/2 for little m, my x bar is equal to capital M sub y over little m, which is equal to 2 times the integral from 0 to the natural log of 2 of the integral from e to the negative x to e to the x of x dy dx. And y bar is given by capital M sub x over little m, which gives me 2 times the integral from 0 to the natural log of 2 of the integral from e to the negative x to e to the x of y dy dx. For x bar, I get 2 times the integral from 0 to the natural log of 2 of x times the quantity e to the x minus e to the negative x dx. This becomes 2 times x e to the x minus e to the x plus x e to the negative x plus e to the negative x, evaluated from 0 to the natural log of 2. I plug in those limits of integration and simplify, and I get 5 times the natural log of 2 minus 3. For y bar, I get 2 times the integral from 0 to the natural log of 2 of 1/2 times the quantity e to the 2x minus e to the negative 2x dx. This gives me e to the 2x over 2 plus e to the negative 2x over 2, evaluated from 0 to the natural log of 2. I plug in those limits of integration and simplify, and I get 9/8. This tells me that my coordinates for my center of mass, x bar, y bar, are given by the coordinates 5 times the natural log of 2 minus 3 and 9/8. I draw my region, clearly labeling the boundary curves y equal e to the x, y equal e to the negative x, and the vertical line x is equal to the natural log of 2. My center of mass is located slightly above y is equal to 1 and slightly to the left of x is equal to 0.5. Let's work another example. I want to find the coordinates of the center of mass of the region specified by r is equal to the set of all xy, such that 0 is less than or equal to x, which is less than or equal to 1, and 0 is less than or equal to y, which is less than or equal to 5, where the density varies according to the density function rho of xy is equal to 2 times e to the negative y over 2. My total mass, little m, is equal to the integral from 0 to 5 of the integral from 0 to 1 of 2e to the negative y halves dx dy. This gives me the integral from 0 to 5 of 2 times e to the negative y halves dy, which is equal to 4 minus 4e to the negative 5 halves. X bar is given by 1 over 4 minus 4e to the negative 5 halves times the integral from 0 to 5 of the integral from 0 to 1 of 2 times x e to the negative y halves dx dy. This gives me 1 over 4 minus 4 times e to the negative 5 halves times the integral from 0 to 5 of e to the negative y halves dy. I do that integral and plug in the limits of integration, simplify, and I get 1/2. Y bar is equal to 1 over the quantity 4 minus 4 times e to the negative 5 halves times the integral from 0 to 5 of the integral from 0 to 1 of 2y e to the negative y halves dx dy. This gives me 1 over the quantity 4 minus 4e to the negative 5 halves times the integral from 0 to 5 of 2y e to the negative y over 2 dy. I integrate this using integration by parts and simplify, and I get 2 times e to the 5 halves minus 7 over the quantity e to the 5 halves minus 1. My coordinates x bar, y bar are therefore given by 1/2 and 2 times e to the 5 halves minus 7 over e to the 5 halves minus 1. I will warn you, you have to be careful with your signs in using the integration by parts here. Now you get to try it. Pause the video and find the coordinates of the center of mass for the upper half of a disk bounded by the circle x squared plus y squared is equal to 4 with a density function rho of xy that is equal to 1 plus y halves. When you're ready, restart the video to check your understanding. In order to find the center of mass for the upper half of this disk, I want to see if I can take advantage of some symmetry. This will be easier to work with if I convert it to polar coordinates first. Rho of xy is equal to 1 plus y over 2. In polar coordinates becomes rho of r theta, which is equal to 1 plus r sine theta over 2. X squared plus y squared is equal to 4 becomes r squared is equal to 4. The upper half of a disk gives us limits of integration from 0 to pi on theta and from 0 to 2 on r, so that my total mass, little m, is given by the integral from 0 to pi of the integral from 0 to 2 of the quantity 1 plus r sine theta over 2 times r dr d theta. I'm going to compute that integral from the inside out. I get the integral from 0 to 2 of the quantity r plus r squared sine theta over 2 dr, which becomes r squared over 2 plus r cubed sine theta over 6 evaluated from 0 to 2. This becomes 2 plus 4/3 sine theta. Now I plug that in as my integrand to my outer integral. I get the integral from 0 to pi of 2 plus 4/3 sine theta d theta. I integrate that, plug in my limits of integration and simplify, and I get 2 pi plus 8/3, or I can write it as 6 pi plus 8 over 3. Now I know what my total mass is, and I also notice that my region is symmetric about the y-axis. This tells me that x bar will be at 0, so I only need to compute y bar. Y bar will be equal to 3 over 6 pi plus 8 times the integral from 0 to pi of the integral from 0 to 2 of r sine theta times the quantity 1 plus r sine theta over 2 times r dr d theta. I distribute the r to compute my innermost integral, the integral from 0 to 2 of the quantity r squared sine theta plus r cubed sine squared theta over 2 dr. This gives me r cubed sine theta over 3 plus r to the 4th sine squared theta over 8 evaluated from 0 to 2. I get 8/3 sine theta plus 2 sine squared theta. This becomes the integrand in my outer integral. The outer integral is the integral from 0 to pi of the quantity 8/3 sine theta plus 2 sine squared theta d theta. I get negative 8/3 cosine theta minus the quantity sine theta cosine theta minus theta evaluated from 0 to pi. I plug in the limits of integration and simplify, and I get 16/3 plus pi. Y bar is equal to 3 over 6 pi plus 8 times 16 plus 3 pi over 3. This reduces to 16 plus 3 pi over 8 plus 6 pi. My coordinates for my center of mass, x bar, y bar, is equal to 0 and 16 plus 3 pi over 8 plus 6 pi. This is how I can compute the coordinates for my center of mass for objects in 2 dimensions. Be sure and let me know if you have any questions.